Okay, so I'm going to talk about configuration spaces, and just to make sure that we're on the same page, let's see, you start with N. This is loose manifold, and now boundary, and then you can define the configuration space of k ordered points, and for this talk I write to twiddle over to ordered. This is given by a set of k points in M, and as a condition that says that they all have to be different. So they are different unless I equal to J for that. Okay, and then then you have a symmetric group acting on these. You can permute the points, and you can define the configuration space of unordered points. So this is just what you get here. Oops, conf km, and you divide out by the symmetric group. Okay. So now these are sort of Okay, so I got into this because the relational configuration space with vortices. So, I mean, as I assume you know, the configuration space of vortices on a Riemann surface is can be identified with configuration space of as many points as the degree of the vortex. Okay, and now at the time, Nuno was thinking about generalizations of this, where you had more than one type of vortex. So that a vortex might not, if you have some points on N, and you have a second class of points, then you can have two rules. So these points, they are not allowed to coincide, and those are not allowed to coincide. But you have a choice. Maybe these are allowed to one of these are allowed to coincide with one of the others, and maybe not. So this can be formalized with a graph. So gamma is a graph. We say k vertices. And now you define, and you also have a number associated to this. So let's see, you have a function, let's call it alpha, from gamma to positive, non-negative integers, which tells you how many of these points you have to pick for each vertex. So the vertices of the graphs, they correspond to classes of points, and this tells you how many there are of each point. And the configuration space you define, this is now given by saying you take x vi, where V is a vertex, so it defines a class.
So this alpha is from the vertices of gamma, right?
Sorry, yeah, thank you. Okay, so for each vertex you have alpha V points, and these are all points of M. And now the condition is that xi xi is different from xvi is different from xvj, wj, if either v is if they belong to the same class, or v and w are joined by an edge. Okay. So let's take some examples. So if you have, for instance,
sorry, I have one question. In the definition of conf gamma of m, so the points are denoted x via a, okay, alpha of v, no?
Sorry. Yes. So if you have, say, this graph, so you have 3 vertices, and you pick one point in each class. So this corresponds to 3 ordered points, because they are ordered by which vertex this is, which all have to be different between these are all connected by edges. So here, configuration space of this gamma, this is simply the ordered configuration space of 3 points in M. And you could also take, for instance, gamma has to be 1 point, and 3 1 vertex and 3 points at this vertex, and then the configuration space, this would be the unordered configuration space. And you could also be, say you could take just 3 points in the vertices, and then configuration space, this is just the okay. So now, of course, you can pick manifolds of different dimensions, and that makes a difference. So let's, for the rest of the talk, let's say that the dimension of m, this is n, which is even, and n is at least 4. Dimension m equal 2, that is of course interesting, especially in connection with vortices. And I have a couple of papers with Nuno on that. Because in that case, you have a fundamental group entry. If n is greater than or equal to 4, the fundamental group plays a much smaller role. I mean, there will still be one, but it will not be so complicated.
Excuse me, in the definition
so
of...
let's assume this for now.
In the definition of conf gamma of m, maybe you want to divide by the product of the symmetric groups.
Yeah, I think it's... So, I mean, the idea is that,
Yeah.
So we the first, maybe I'll explain a little bit. So you have a graph, and then it's like each vertex is supposed to represent one type of vortex. For example, when there's one point, it's basically, you can think of it as maybe vortices on the line bundle.
Yeah.
Right? And then conf n, you know, there's a way of understanding the to be the symmetric product of n. Yeah. So this is some inequalities.
So now there's a special case where you take m to be Rn. So now you have points in Rn, and there is, if you consider the ordered configuration space, you can organize this into an operand. So how does this work? So if you have, so this means you want something from, say, conf 2 as an example, close configuration space Rn, close configuration space, and this will all have triggers, Lrn, and this goes to configuration space K plus L Rn. So a point here, so that's 2 points in Rn. So here you have K points in Rn, and here you have L points. And now what you do is put this into the first slot here, and this in the second. And these have to be ordered because you have to know which of these factors has to go there and which factor has to go there. Okay, so this is a pretty well-known opera. It's essentially a little disc opera, no?
Sorry, but this is defined only up to homotopy, well defined only up to homotopy, I imagine, no? Because if I understood well, you have to shrink the...
Yeah, you do. Yeah, you do some. Right. You have to shrink. Right. You have to shrink these things. So there are some technical stuff which I was hoping to be able to ignore, but you're completely right. Okay. So now this is also relevant, for instance, for these. For these unordered configuration spaces, which are relevant to Vortices, because this operand acts on the unoriented configuration space, essentially by saying, I mean, if this could be unordered as long as this one is ordered. So this gives you an operation. Okay.
One question more. In the definition, I cannot read. But is it the case that vortices corresponding to either to the same vertex or to the vertices connected by the edge, they're not allowed to collide?
Yeah. If you have an edge, so each vertex defines a class, and if you have an edge, the points in those two classes are not allowed to collide.
So yeah. So the vortices. So when you have high multiplicity in a vertex, they are allowed to collide.
They're not.
So it's not really what is written there, but anyway.
Allowed?
They are allowed to collide.
In the same
point of M.
Yeah.
If they correspond to different vertices, but there is no edge.
Oh, yeah,
again,
sure.
Again.
Yeah. Right.
Only if there is an edge in the graph, they are not allowed. And then there's an inequality.
Yeah.
But
can there be a self-edge?
Yeah. So this is
Well,
if they are joined by
an
an edge. Yeah. Okay.
Is there like some motivation for this definition? What?
it comes from looking at vortices on surfaces, with targets which are toric varieties, and then the polytope basically, the faces will correspond to the vertices of the graph, and basically, so there's some direct motivation for this problem of vortices on a Riemann surface with a target which is a toric manifold.
Okay, so here's the graph. And three vertices, and you have edges here and there. And then what you're allowed, these are not allowed to collide with those, but these are allowed to collide with them. So something like this, and these two could be at the same point.
And so the same labels are allowed to collide with themselves.
So if they have the same type, they are allowed to collide. They are allowed, right?
No. Wait.
So there are two types of. So your edge means that they cannot collide, right?
Yeah.
Okay. So I think that the way we usually work is that the vortices of the same type they can collide, right? So the model space of vortices on the line bundle is a symmetric product.
Yeah. I know. Oh wait, what am I saying here? Yes, of course it's symmetric product. Shit.
Yeah.
So just erase either V plus W.
Yeah.
So the simplest problem is the graph, which is just one vertex, And then you can put some multiplicity, some integer, and this means that you are doing a symmetric product of that multiplicity. Okay? So this means that, yes, they are allowed to collide on the surface. The simplest way, when you have something which, where there are restrictions, is the graph with two vertices and an edge. So these actually vortices we target P1, and then so the configurations will be parameterized by an effective divisor of zeros and poles of the section. So whenever you have a zero in a point, you cannot have a pole, so they're not allowed to collide. So this means that there's going to be some kind of, this is more like a configuration space, and there's going to be this kind of inequality.
Can I think of one last question? Can I think of this graph as actually some quiver gauge theory that realizes this? No.
I think it's the intersection pattern of the divisors.
It's something that you can easily read off from the Nelson polyton. You say you have to dualize and then take this one skeleton. So that's the graph we're talking about.
Okay. So, so now there are methods for studying these little disk operands. So you have this trick by Kontsevich. So you construct a DDA, and now you make a map of this into the RAM cohomology of the configuration space. So this is now the oriented one, the ordered one. So, okay, so how do you do this? So you start with configuration space with k points, and then you add some other points, and you construct an integral which essentially measures the degree of one point going around another, and you integrate. So this is an integration map. Okay, I should say what CK is. CK is Q vector space, and bases are graphs, and these graphs they have exterior and interior vertices. So there are rules for this. There's a graph like this. So you have four exterior vertices and perhaps two interior. And the first rule is that each of these interior vertices has valence at least 3. Okay. And then you can have some exterior. So this is an exterior edge, and all of these are interior edges. Okay. So now you construct an integral on a larger configuration space, where also these points, these vertices corresponds to points, and then you integrate over these points. And it turns out that this gives you, it gives you a map. And there are problems there because you have to check that these integrals converge, and that's sort of tricky business. It's also this is also a map of GGAs. So what is the multiplication rules? Yeah. If you take this, you multiply to that. First, you just add the external edges and the internal edges. You just add a union. So this goes to here, and that goes to there. And if you could get a double edge here, and they are 0. Okay, and differential.
So is the number of external vertices fixed?
Sorry?
Is the number of external vertices fixed?
No.
So then how do you find a correspondence between the vertices?
So this, this is in homological degree 1. That's one external vertex. This is in homological degree 2. And the differentials, they go from higher homological to lower homological degree. And they are given by collapsing. So collapse each edge and add. So for instance, if you have this goes to a sum of 3. You can see this and this and this. And there are also some signs involved, which I prefer not to talk about. And actually, if you're careful, you should. So each of these graphs comes with a sign, with an orientation.
So for the multiplication, right, so a priori this graph could have an automorphism, right? Or like, you could reorder the edges and then it looks like the picture would be different if you reordered the edges in one of the graphs.
Well, okay.
Sorry, the vertices.
So, good point. So the exterior edges, they are fixed. So you look at these as isomorphic classes, huh? Isomorphic classes of graphs where the outer, where the exterior subgraph is fixed.
I see.
Yeah. Okay. So now you want to relate this to this other feature. And okay, so the reason I was confused about this is really that I mainly think about the case where you have, and the first step is to think about the case where you only have one point of each color.
Right.
Yeah. So let's say, so from now, 1 point of each color. So in the language before, you could have something like this. No? So you have 1 point in each, and these two are not allowed to collide, but these two are allowed to collide.
So by the way, this word color means the type of vertex.
Okay. So, yes. So now you look at this. Now there's a theorem which is purely algebraic, which computes the homology of CK. So this is concentrated in degree 0, and in degree 0 it's actually the same as homology, well, de Rham homology of M. For star equal to 0 is equal to some de Rham homology of M. Okay, so in particular this map here, this can't really be the map from CK to here. This does not exactly preserve degree, but there's a formula. So and H, so HCM. So phi from Cn to H to Rham star, this induces isomorphism on, let's say, real homology. So this map is this is a quasi-equivalence. On the other hand, this guy, this is formal. So it's homotopy equivalent to its homology because the homology sits in degree 0. So you have a map to the 0 homology, and this happens to be an isomorphism. Okay. So this is all, most of it is Kontsevich, and there are other people involved. And now my project is to use this to see if I can get information about the real homotopy type of these configuration spaces of graphs. Okay. So you can, so now you have, so a generator for CK, a base element in CK. This was one of these graphs. And now it could happen. Okay, so you take, so gamma, this sits in a complete graph with as many vertices as gamma has, no? So you have this inclusion. So this is included in whatever. So this gives you a sub-algebra of CK. So you can define CK of gamma. So this is vector space generated by graphs with exterior subgraph contained in Rham. So you know you're only so now you're looking at a sub-vector space of CK, and it's generated by those graphs which don't have any edges, which are not edges of gamma. Okay, so this algebra not closed on the differential, which you can see clearly in this example, huh? Because if gamma is just as this single edge, this would be an element in CK of gamma, and the differential, this would contain all of this stuff everywhere else. So now you can try to define something else. You take this to be the C in CK of gamma, which satisfies that the boundary of C is also in CK of gamma. And the boundary is now taken inside this complete thing. Huh? So it's this boundary. now you can. This is a little smaller than CK, of course. But here's an example. Suppose you have this, and then you rotate it cyclically. This, and you take the boundary of that, and yeah, I guess you should fill in this too. So now all of these graphs can be different. They have something which is not contained okay, but all in all, this is equal to this element, and there are some signs which I will not go into. So it's the sum of these four graphs which are in C naught. Okay? So, and this is what I propose as substitute for CK in the this not. So now you take
Can you say again, what was CK without gamma?
Okay, so CK or gamma, these are generated by the graphs such as the exterior part of them
CK
is
without
containing gamma. So these are graphs which are in CK of the complete graph.
So it's a vector space generated by the set of graphs.
Okay, but then I don't know. There's like statement about homology of CK.
Okay, so
how can
yeah,
H0
okay,
be?
so there are two things here. This is a gamma. So this CK here, this is the original one defined by Conserich, which should be C of a complete graph on K vertices. No? So the original case, this corresponds to my complete graph. Okay.
So when there is no graph, it means that it's the complete graph, and this is the case that was considered by Conserich.
Yeah.
Complete graph means you choose your vertices, then you connect all the vertices with all the possible edges.
So CK is a vector space generated by.
CK is vector space generated by all graphs with K or isomorphic classes of graphs with K exterior vertices and a number of unordered internal vertices. And yeah, and then you can, well, then there are some conditions like the internal vertices must have variance at least 3, so this would be an example then. And now I'm defining relative to gamma, I'm defining a sub-TGA of that. I mean, if you check this, you can see it's, yeah, it's an algebra. So now you have this CK gamma, and you want to prove some things. So first you want to prove that H naught, this is the configuration space of gamma of Rn. And secondly, you want to prove that the higher homology groups, they are 0 for E I greater than 0. And 3, you want to prove that CK, that there is a map to the de Rham cohomology complex of configuration space of gamma m and R n. And if you can do all this, you can copy concierge ID. So you get that this this configuration space. This is you determine the rational homotopy type of it, and in particular, it is formal.
So what is the statement in 3?
Well, there is such a map, and that it induces isomorphisms. Well, it induces this isomorphism.
So on the right there should be H0 or H star, H star.
Well,
for number 1.
well, I mean, no. This is a map of DGS.
For number 1. For number 1.
This
So
should
it's sum of
be H star now.
Yeah.
Because I mean, this is homological degree 0, and of course you have another grading here, which is not. Okay. So where are we? So I can actually prove this. And this here, yeah, I have written down a proof which I'm not completely confident of because it's rather complicated. And I think, how much time do I have? Yeah, I think I'll say more about that. Also, of course, you can do computer calculations here, but the computer breaks down pretty fast because there are so many graphs. And the computer calculations tend to support this. This, I think, is pretty similar to the map concierge constructs. I haven't checked all details, but I'm pretty confident. Okay, so this would give formality of these things. Now, there's another thing here. I mean, it's nice to know that the spaces are formal, but you also have this operate structure. And there's a fourth thing here. You have an operate structure compatible with phi. And I guess then I should, so, I mean, I explained what the operate structure was in the little disk case. And now, of course, you can do something similar where you don't use little disk. I mean, you use these little disks of various classes. And you can write down an operad-like theory for this.
Is it going to be a colored operad?
No, I don't think it's. I hoped so, but I don't think it is.
So it's something that's a little
Yeah, I mean, it's some similar ideas, but I don't think it's exactly that.
I see.
But you can combine them in some way.
Yeah, so it's an operad over an operad that's not
Yeah.
universal operad.
Yeah.
But related.
Fast. Okay. So and this map should be compatible with that. So that would mean that you have something, some formal, that this operad in some sense would be formal, whatever it means for this generalized type of operads. Okay, so I guess I'll spend just a little time on explaining why I think, or why this homology equals the homology of configured space. Yeah, you see, you can compute cohomology of the cohomology H star of configured space gamma. And you can do it in various ways. I mean, people have been doing this using identifying this with complement of arrangement of hyperspaces. And you can do it in other ways. So the answer is that this is an exterior algebra in generators in degree. So yeah, EI. ER is gamma, and there's a number of relations, and these relations, they are given in the following way. Each time you have a cycle. So this is a cycle in gamma. Then you can write down. So these correspond to some of these classes, and then you can write down a sum, and let's see, depends on there's some sign here, and then you take your product of all of them except one. How many did I say? Say they are. Yeah, here there are 5. So let's keep it 5. So a cycle gives a relation of this type. And I mean, they were first seen by Arnold many years ago, so that's why I call them A. And now you can prove by algebra, you can show that if you form this corresponding thing for, so if you form this ring here, which we now know what it is, then it injects into the homology of configuration space of the complete graph. I mean, this is a non-trivial algebraic statement, but it's true, and it's proved. Yeah, I proved it with Erika Minus, and maybe people knew it before. And there's another thing. You have a map from lambda of the edges to this. And I mean, that was what I talked about before. So if you have an edge between 2 points xi, xj, and this is all in Rn, then you can pick, and these are different, you can pick the vector between them. This gives you an element in Sn minus 1, so it gives you an element from configuration space of gamma to Sn minus 1, and you pull back to the fundamental class. So this gives you a class EI, and this map is selective. I mean, these are the same as those. So now, using these things, it turns out that by pure algebra and rather simple algebra, you show it's enough to prove that H naught of Ck gamma is equivalent, is isomorphic to the homology of this configuration space. It's enough to check that you have a map from lambda E1 to EL. This is actually the same as C naught of gamma. Because what is C naught? C naught, this is generalized by graphs with 0 exterior vertices, 0 interior vertices. So it's just a subgraph of gamma. So this means that the 0 part of this DGR, this is just exterior algebra. Okay. And it's enough to check that in this group we have A, and that is in in the image of D from C1 gamma to C0 gamma. So this together with the algebraic factors proves that. And now here I wrote down an example somewhere. So if you take this and rotate this and add another one, we get exactly the NR class. So this proves it for, so by construction of C in R0 in R1 gamma, so that DC is an NR class. And you have to do it for each NR class, so every cycle gamma gives you one. Then proof follows. No? So now we have to construct these classes, and I mean they are not uniquely defined because they are only defined up. They are only well defined up to a boundary, so they can be a little too hard to find. And I mean the formula I wrote down, I talked about, which I wrote down. This is a explicit formula for one element, but it's not unique. No? And I have a feeling that there must be smarter ways to prove this.
So what did you write? So is it DZ?
Yeah, so okay.
Easy
So
now.
this is a particular element in here, namely that one. No?
Yeah.
And you want to show that this, so this is 0 in the homology. So you want to show that this element in here goes to 0 over there.
Mm-hmm.
This means that in homology it goes to 0 over here. This means exactly that it's a boundary. No?
Mm-hmm.
And now you have a combinatorial problem. Can you find such a C? And I believe that I can, but I don't promise it completely. And I mean, I checked it on computer up to, up to at least 8 vertices or so. But, okay. So then, the more tricky problem is probably this. And it turns out that, I talked for, yeah, okay, I can say this. So, in the original Kontsevich case with a complete graph, where you can prove this by using, you can find some explicit chain homotopics, which shows it's 0. But these chain homotopics, that I've worked hard on trying to make them work for gamma, but it seems they have a tendency of going outside the ring. So I can't. So I can't say anything definite here except that the computer tells me it has a chance. Okay, so I think I should stop there. Thanks for your attention.
So we have actually maybe a few more minutes for questions, and then we'll take a break. So any questions?
So the stage you are at, this is still with the just weights 1, right?
Yeah, I mean this is okay.
Yeah.
These are.
So is 1 okay? I mean,
1 is okay, and 4 I think is okay. 2 is. Yeah. 2 is, I think, the most problematic one, actually. But it's still a combinatorial problem. 3, I think, should be okay, but I haven't written down details.
So I guess I have a combinatorial question. So you said they don't quite form a colored operad. But so let's say that I want to include one configuration space as a vertex of another. Do you just take the graph of the new one and connect it to all the edges?
Yeah, I mean,
connect it to all the edges.
Yeah, I mean, you have some classes here, no? So here you have 2 types, and here you have perhaps 2 others, no? And then you have a graph which better have ordered vertices now. But I guess, yeah, it has now because we already have 1 point of each. So then I mean, just like in the little disk opera, I mean, I use these two to combine those. And now I have 4 classes. And there are some of these are allowed to collide and some are not. And there's some combinatorics involved in this, but it's not, it's no big.
Yeah, something like if.
You have to keep, this just keeping track of it.
Any other questions?
So these things that you, for example, 1, let's say property 1,
Yeah.
when you have a gamma, you now, instead of having weights 1, just some of the weights not being 1.
Yeah, I haven't thought so
You haven't
about
thought
that.
about it,
Yeah, because I mean, the last year or so, if I have thought about this, I have thought about this case
Yeah,
one,
okay.
and okay, which reflected unfortunately on my presentation.
Okay. So, thank you, and I guess we can probably take maybe 10-minute break until 6:25. I guess the thing I was telling you